This is the first of 4 videos for our next class, and in these videos we'll talk about the passive membrane properties of neurons and how action potentials are propagated down the axon. In order to understand how action potentials are actively propagated down the length of an axon, we first have to investigate the passive membrane properties of neurons. When a synaptic potential is generated in a dendrite, it is conducted through the dendrite to the soma by a passive process. It is conducted passively, and this process, this passive conduction, is called electrotonic conduction. And this electrotonic conduction is dependent and determined by the membrane resistance of the dendrite, as well as the cytoplasmic resistance of the dendrite, and also the membrane capacitance of the dendrite. It's important to realize that this passive conduction, electrotonic conduction, does not depend on the action of voltage-gated ion channels. There's no regenerative amplification of the potential as it is conducted down the dendrite. So electrotonic conduction is important, as I've mentioned, for the conduction of synaptic potentials through dendrites to the soma, and it determines both temporal and spatial summation of synaptic potentials. Together, this is called synaptic integration. And as we'll see, passive conduction, electrotonic conduction, also plays an important role in the propagation of action potentials through axons. It plays an important role in determining the conduction velocity of propagated action potentials. One of the key concepts in understanding the passive membrane properties of neurons is the membrane time constant. When the a current is injected into a neuron, or when ion channels open, allowing currents to flow across the membrane potential changes, and the time course at which the membrane potential changes is determined by the membrane time constant. In order to understand this and to illustrate this, we will turn back to our model neuron here. In this case, this neuron contains both sodium channels and potassium channels. We will assume that these channels are voltage independent and that we can open and close the channels at will. We will start our experiment by assuming that the potassium channels are open and the sodium channels are closed. And in this case, we know that the membrane potential of this neuron will be at the potassium equilibrium potential. Now at this point here, we will open the sodium channels but keep the potassium channels open as well. And the question that we'll be investigating is, how does the membrane potential change? How does the voltage change as a function of time? Well, again, before the sodium channels open, we're sitting at the potassium equilibrium potential. There's no net flux of potassium through the open potassium channels. When we open the sodium channels, there will be an initial influx of sodium because sodium is higher outside than inside. So sodium ions will flow into the cell, bringing a positive charge into the cell, and this will depolarize the neuron. So initially sitting at EK, when the sodium channels open, the membrane potential will begin to depolarize as sodium ions flow in. Now as the voltage moves away from the potassium equilibrium potential, this will now generate a driving force for potassium to move out of the cell, where we have moved away from the potassium equilibrium potential. Thus the relative positive charge inside will cause potassium to flow out. So initially when we open the sodium channels, the cell depolarized, but as we move away from the potassium equilibrium potential, potassium will start to flow out, making the net influx of charge less, and so the depolarization will slow up, And then as we move farther and farther away from the potassium equilibrium potential, the depolarization will slow even more until we reach a steady state potential where the influx of sodium will just equal the efflux of potassium. We know that this steady state potential can be determined, calculated from the Goldman-Hodgkin-Katz equation, and it will be dependent on the relative permeability of the neuron to sodium and potassium. Once we reach the steady state potential, the voltage will not change until we change the relative permeability of the membrane to sodium and potassium. And at this point here, corresponding to this point up here, we're going to close the sodium channels again, and only the potassium channels will remain open. Now potassium will leave the cell. There'll be an efflux of potassium because the voltage inside the cell is more positive than the potassium equilibrium potential. This efflux of potassium will cause the membrane potential to become more negative. We approach the potassium equilibrium potential again, and as we approach the potassium equilibrium potential, there'll be less and less of a driving force for the potassium, and this driving force will then go back down to zero as we actually reach the potassium equilibrium potential. Now the question is, what is the time course of the change in membrane potential as we opened up the sodium channels and then as we close the sodium channels once again? Well, we can calculate what this the time course of this voltage change will be by constructing an electrical circuit, an equivalent circuit representing the membrane resistance and the membrane capacitance. So in our model, we had potassium channels that were open. This can be modeled by a resistance across the membrane, and also the membrane has a certain capacitance. We can model this by a capacitor, and if we draw the equivalent circuit, the resistance here represents the potassium channels that are open. The capacitance represents the membrane capacitance. This battery here represents the potassium equilibrium potential. And then there's one more component of this circuit, which is Im, which represents the sodium flowing into across the membrane when sodium channels are open. And in order to determine how the voltage of the cell changes with time, we can solve for current flow through this circuit and come up with an equation that describes this current flow. And we're not going to go through the derivation of the equation, but we will just display here the solution, which tells us that the membrane potential equals a certain maximal potential that the cell will depolarize to times 1 minus e to the minus t over tau. T represents time, and tau represents a specific time constant that tells us how quickly the voltage is changing. This is the first order exponential equation, and if we solve it for time, we find that the voltage changes in a shape that looks like this, where when we open the sodium channels, the cell depolarizes. That's shown here. The maximal voltage change is given by this term here, Vmax, and then when sodium channels close again, the voltage drops back down. This is showing the injection of current, or we can think of this as the sodium channels being closed here and the sodium channels being open here. Well, this is useful. We now know that when we open up channels, or we activate a synapse, for instance, and open up ligand-gated channels, which are permeable to sodium, we now know that the voltage in the cell will change as a first-order exponential, described by a first-order exponential equation. But what we'd really like to know is how quickly this voltage changes, and that is determined by the time constant tau. And it's determined in a way that is shown right here, where this exponential curve has a time constant which is defined by tau, and if we look at the time it takes the membrane potential to reach 1 over 1 minus e, that time it takes is given by the time constant. If we solve for 1 minus 1 over e, we find this is approximately 63%. So if we want to define the time constant, that is the time it takes for the voltage to reach 63% of the final voltage. So that value is here, and the time it takes is tau. Well, that's all nice and good, but it would really be useful if we could calculate what the value of tau is. Well, it turns out that tau equals the value of the membrane resistance by the membrane capacitance. Tau equals R times C. So if we know the resistance of the membrane and we know the capacitance of the membrane, we know what the time constant is, and we know how quickly the voltage of the cell will change when we open up ion channels. We've seen that the membrane time constant equals the membrane resistance times the membrane capacitance. Well, what are these two values? Well, membrane resistance is simply defined by the number of ion channels that are open. If there are no ion channels in a membrane, it will have a very high resistance. As we open more ion channels, the resistance will go down. Membrane capacitance is a parameter that defines the capacitance that is generated by the membrane of a neuron. A capacitor in an electrical circuit is simply an insulator that separates two conductors. And a neuron, just like all cells, acts as a capacitor because the lipid bilayer functions as the insulator, and the extracellular and intracellular solutions function as the two conductors. This is a somewhat difficult concept, but there is one relation that involves the membrane capacitance which is useful to know and will help you understand the importance of the membrane capacitance. And this relation is given here, which says that the membrane potential, Vm, equals the Q, the charge difference between the inside and the outside of the cell, divided by the membrane capacitance. So we know that the larger the charge difference between the inside and the outside of the cell, the larger the membrane potential. But the question is, what is the relation between the excess charge inside the cell and the membrane potential? And that relation is given by the membrane capacitance. So if we know the charge difference, the number of excess positive or negative charges inside the cell, and we know the membrane capacitance, then we know the membrane potential of the cell. Let's look at examples of the membrane capacitance and resistance. First, we define a term called the specific membrane capacitance, which is the capacitance of the membrane per unit area, and it's useful to define the capacitance per square centimeter. Capacitance is given in terms of units of farads, and so the specific membrane capacitance is has units of farads per square centimeter. And very conveniently, because all membranes of cells have approximately the same structure, the membrane capacitance, the specific membrane capacitance of a cell, of all cells, is constant, and it equals approximately 1 microfarad per square centimeter. So we don't have to worry about the membrane capacitance, the value of the capacitance changing. It's a constant, and it equals approximately 1 microfarad per square centimeter. The same is not true of the membrane resistance. The resistance, as we've discussed, depends on how many ion channels are open. The units of resistance are ohms, and again, it's useful to define a specific membrane resistance, which is the resistance of the membrane per unit area. The resistance is given in units of ohms centimeters squared. We don't have ohms per centimeter squared because as the area of a membrane goes up, the resistance actually decreases. So the units of specific membrane resistance is ohms centimeters squared, and it can vary quite a bit depending on how many channels are open, and it can vary from anywhere from about 1 to 100,000 ohms centimeters squared. Let me just remind you that there is a reciprocal relation between membrane resistance and membrane conductance. They're very simply reciprocal of each other. Resistance has units of ohms. Conductance has units of Siemens. And just to give you one example of membrane resistance and capacitance, this represents a typical dendrite where the membrane resistance will be about 10,000 ohms centimeters squared. The membrane capacitance, of course, is 1 microfarad per centimeter squared because it's a constant. And then if we calculate tau, we find that tau, which as you will recall is given by the equation R times C, membrane resistance times the membrane capacitance. If we multiply 10,000 ohms centimeters squared by 1 microfarad per centimeter squared, the 2 centimeter squareds cancel out, and we end up with a value of 10 milliseconds. If we look at the units of ohms centimeter squared times farads centimeter per centimeter squared, the units turn into milliseconds, and we have a value of tau of approximately 10 milliseconds, which is a good representation of the time constant of a neuron, the soma or dendrite of a neuron. In order to understand the importance of the membrane time constant, we'll be doing an exercise in class that considers the generation of postsynaptic potentials that are generated following the arrival of action potentials at the presynaptic terminal. So please read through this exercise and think about it, and we will discuss the solution of this exercise in class.